Hello friends, today we are going to discuss about molecular orbital theory, that is M.O. theory. You will also get the PDF in your description box. Condition for linear combination of atomic orbital or important features for molecular orbital theory. In order that atomic orbital may interact and form molecular orbitals, three conditions must be fulfilled. These are: number 1, the atomic orbital must have comparable energies. Number 2, they must overlap appreciably. Number 3, they must have same symmetry with respect to the bonding molecular axis. We will discuss about these three conditions in the next slide elaborately. First condition: atomic orbital having large difference of energy will not combine to form molecular orbitals. Thus, in elements of the second row of the periodic table, that is lithium to neon, the 1s atomic orbital is far below the 2s and 2p atomic orbitals and do not form molecular orbital with them. Similarly, the s and p atomic orbitals do not combine to form molecular orbital in the homonuclear diatomic molecules when their energy difference is large. Second condition, which says that the combining atomic orbitals must overlap to a considerable extent. Repeatedly I say, the combining atomic orbitals must overlap to a considerable extent. The greater the overlap of the atomic orbitals involved, the greater will be the electron probability density between the two nuclei. Third condition, which says that atomic orbitals of comparable energies would combine only when they have the same symmetry above the internuclear axis. Repeatedly I say, atomic orbitals of comparable energies would combine only when they have same symmetry above the internuclear axis. We shall soon appreciate that an s orbital cannot effectively combine with a px or py atomic orbitals if the molecular axis lies along the z axis. Two atomic orbitals produce two molecular orbitals. Two atomic orbitals produce two molecular orbitals, one of which has an energy lower than that of the lower energy atomic orbital, and the other has an energy higher than the higher energy atomic orbitals. The lower energy molecular orbital is called bonding molecular orbitals, and the higher energy orbital is called an anti-bonding molecular orbitals. Thus we can easily calculate the bond order. Bond order is equal to half into the number of electrons in the bonding MOs minus number of electrons in the anti-bonding MOs. The valence electrons are distributed among the molecular orbitals the same way as in the atomic orbital. Each molecular orbital can accommodate a maximum of 2 electrons. Same as the atomic orbitals, electrons occupy lowest energy molecular orbital. Higher energy orbitals will not be filled up as long as the lower energy molecular orbitals are available. When two equal energy molecular orbitals are available, electrons will tend to remain unpaired so long as they can avoid pairing, because pairing produces extra energy which unstabilizes them. Here you can see, here in this slide and this slide, you can see the representation of M.O. diagram of homonuclear diatomic molecule. Here 1s and 1s, two atomic orbital 1s and 1s combine each other to form lower energy bonding orbitals, which is represented by sigma 1s, and another is anti-bonding orbital, which is also represented by the sigma star 1s. Here you can see the molecular orbital representation which have the with sp interaction. Here 2s atomic orbitals 2s and 2s atomic orbitals similarly as the 1s and 1s atomic orbitals. Here you can see the 2s 1s and 1s, two 1s atomic orbital combine each other to form sigma 1s and sigma star 1s. Here also the 2s orbitals, two 2s orbitals combine each other to form sigma star, one sigma star sigma sp1 and another is sigma star sp1. Here the px, py and pz orbitals, atomic orbitals are present and they combine each other to form pi to py, pi to pz, as well as sigma sp2 and sigma sp2, as well as the pi star to py and pi star to pz and the sigma star to sp2. This type of diagram is this type of diagram can be represented for lithium to nitrogen, because their s and p orbitals, the energy gap between the s and p orbitals is so small. So I finish here this video. Okay.